Settle in. Let the weight of your body sink into whatever is holding you. Let your shoulders drop just a little. Let the tension in your jaw release. Feel the warmth of wherever you are, the familiar comfort of your bed, your couch, your chair, and let yourself arrive here, fully, in this quiet moment. Because tonight, we are going to explore something extraordinary. Not extraordinary in the way of explosions or breaking news or things that demand your immediate attention. Extraordinary in the quieter, deeper sense. The sense that makes you stop in the middle of an ordinary afternoon and stare at nothing. Because a thought has just arrived that won't let you go. The sense that the world is older and stranger and more wondrous than you had remembered. We are going to talk about things that shouldn't exist, not in any supernatural sense, not in any way that requires us to abandon reason or evidence or careful thinking. Simply in the sense that when you encounter them, when you hold them in your mind and turn them over and truly consider what they represent, your first instinct is to say, how? How did they do this? How did people without computers, without industrial equipment, without centuries of accumulated modern science, manage to create things that we, with all of our technological sophistication, struggle to replicate or even fully understand? The ancient world is full of these things. There is a small bronze mechanism, roughly the size of a shoebox, pulled from the wreck of a 2,000-year-old ship at the bottom of the Aegean Sea, that turns out to be a working mechanical computer, capable of predicting astronomical events with a precision that would not be matched again for more than 1,000 years. There are stone structures weighing hundreds of tons each, assembled with a geometric accuracy so fine that a human hair cannot be inserted between their joints, built in a desert 4,000 years ago by a civilization that had no cranes, no steel, no wheel, in the conventional sense. There is a form of concrete, mixed by Roman engineers 2,000 years ago, that has been sitting submerged in the Mediterranean for 2 millennia, and is, to the bewilderment of modern materials scientists, actually getting stronger with time. Our best modern concrete begins to crumble after 50 years. There are maps drawn before the age of exploration that show coastlines no European sailor had yet seen. There are batteries, or something that functions exactly like batteries, found in ancient Persian ruins. There are surgical instruments from ancient India that closely resemble tools used in modern operating theaters. There are lenses, ground from crystal, found in contexts thousands of years before anyone is supposed to have understood optics. And behind each of these objects, each of these puzzles, there is a human story. A story of minds working with fierce concentration and patient genius. A story of civilizations that rose to extraordinary heights of knowledge and capability, and that in many cases fell, taking their knowledge with them into the silence of ruin and time. Tonight we are going to follow those stories. We are going to sit gently with the mystery of what human beings knew and made in the ancient world. We are going to explore not just the objects themselves, but the people who made them, their cultures, their methods, their philosophies, their daily lives. And we are going to ask the deeper question that underlies all of these puzzles. What does it mean that this knowledge was lost? What does it tell us about the nature of human civilization? About the fragility of knowledge? About the strange and non-linear path of our species through time? We will not pretend to have definitive answers to every question. Some of these mysteries are genuinely unsolved. Some may never be fully solved. And that uncertainty is part of what makes them beautiful, part of what makes them worth sitting with, in the quiet of an evening, when the mind is soft and open, and ready to wonder. So let us begin. Let the night hold you. Let your breathing slow. And let the ancient world come forward out of the darkness, patient and full of secrets, ready to tell you what it knows. Picture the floor of the Aegean Sea, off the small Greek island of Antikythera. The water here is deep and cold and very clear, the way Aegean water tends to be in the autumn, when the tourist boats have stopped running and the sea settles back into its older self. The bottom, if you could look straight down from a small boat, would be a tumble of pale rock and dark weed, the occasional flash of a fish moving through shadows. Now, go deeper in your imagination. Drop below the surface, below the thermocline, where the water suddenly chills, down to a depth of about 45 meters. And there, on the rocky seafloor, partly buried under centuries of sediment, you would find, if you were diving in the year 1900, which is when a group of Greek sponge divers first found it, the wreck of an ancient Roman cargo ship. The ship had gone down sometime around 65 BCCA. Scholars are not entirely certain where it was coming from or where it was going, though the most probable theory is that it was a large merchant vessel carrying cargo from somewhere in the eastern Mediterranean, Greece possibly, or Asia Minor, toward Rome or one of the great ports of the Italian coast. It was carrying an extraordinary collection of goods, bronze and marble statues of great artistic quality, glassware, pottery, jewelry, coins, the kind of cargo that suggests a ship serving wealthy clients, perhaps carrying plundered art or luxury goods for the elite of the Roman world. Among all of this cargo, there was one object that the sponge divers brought up from the seafloor on that autumn day in 1900, which did not immediately appear to be anything special. It was a lump of corroded bronze and wood, roughly the size and shape of a large dictionary. It was green and black, with oxidation, encrusted with marine growth, clearly very old. The divers set it on the deck, alongside everything else they had recovered from the wreck, and proceeded with their work. Over the following weeks, as the objects from the wreck were transferred to the National Archaeological Museum in Athens, the lump of bronze sat quietly in a corner, largely overlooked. Then, in May of 1902, a Greek archaeologist named Spiridon Stias was examining the museum's collection of recovered objects and noticed something that the others had missed. The lump of bronze had split open slightly along an ancient fracture, and through the split he could see gears. Actual mechanical gears, small, delicate, precisely cut gear wheels made of bronze, stacked and meshed together in a configuration that looked nothing like anything that was supposed to exist in the ancient world. No one at that point had any idea what they were looking at. For decades, the object, which became known as the Antikythera mechanism, named for the island near which the ship had sunk, sat in museum cases while scholars debated its purpose and significance. The scientific and archaeological establishment had enormous difficulty accepting what the evidence seemed to suggest, because what the evidence seemed to suggest was impossible. Slowly, painfully slowly, the truth emerged. The breakthrough came in the 1970s when a physicist named Derek de Solla Price applied X-ray and gamma-ray imaging to the corroded fragments, revealing the internal structure of the mechanism with unprecedented clarity. What Price found inside those corroded lumps of bronze overturned everything the academic world thought it knew about ancient Greek technology. The Antikythera mechanism was a hand-powered mechanical computer. It contained at least 37 interlocking bronze gear wheels, arranged in a configuration of extraordinary complexity and precision. The gears had been cut by hand to tolerances so fine, fractions of a millimeter, that the craftsmen who made them must have possessed both a deep theoretical understanding of mathematics and astronomy, and a practical skill of almost inconceivable delicacy. The mechanism had multiple display faces, showing different astronomical calculations simultaneously, and it was operated by turning a single input shaft on its side. What did it calculate? It calculated the movements of the sun and moon, as seen from Earth, predicting their positions in the sky with remarkable accuracy. It tracked the phases of the moon through a sophisticated gear train that modeled the moon's variable orbital speed, a genuinely difficult mathematical problem that requires understanding what we now call the elliptical nature of lunar orbits. It predicted solar and lunar eclipses using the 223-month Saros cycle that Babylonian astronomers had discovered centuries earlier. It tracked the positions of the planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn, modeling their complex apparent motions through the sky. And it displayed all of this information simultaneously on a device that you could hold in two hands. More recent research, particularly a landmark 2006 paper published in the journal Nature, and subsequent work by the Antikythera Mechanism Research Project, has revealed even more. The mechanism's front dial showed the Greek zodiac and an Egyptian calendar. One of the dials on the back displayed the 4-year Olympic cycle, tracking which year of the Olympic Games was approaching, alongside other Greek festival cycles. Another showed the 19-year Metonic cycle, the period after which lunar and solar calendars resynchronize, which was fundamental to accurate calendar keeping in the ancient world. The people who made this device knew things about mathematics, astronomy, and mechanical engineering that we would not expect them to know. They understood the irregular speed of the moon's orbit. They had a working model of the solar system. They knew how to translate that model into a system of interlocking gears that could perform accurate predictions, mechanically, without any calculation by the user. They had essentially created a planetarium you could carry in a bag. Who made it? The most likely attribution, based on the style of the Greek inscriptions found on the mechanism's dials and the astronomical parameters used in its calculations, points to the island of Rhodes. Rhodes in the 1st century BCE was one of the great centers of Greek scientific and philosophical learning, home to a thriving community of astronomers, mathematicians, and engineers. The great Stoic philosopher Posidonius had his school there. The brilliant astronomer Hipparchus, who is credited with developing trigonometry and creating the first accurate catalogue of the stars, had worked in Rhodes. And there are ancient literary references to elaborate bronze automata, mechanical models of the cosmos, being made by Rhodian craftsmen. One ancient source, Cicero, the Roman statesman and orator, writing around 65 BCE, which is almost exactly when the Antikythera ship went down, mentions having seen a device made by his friend Posidonius that modeled the movements of the sun, moon, and planets. Cicero calls it a sphera, a sphere, and describes it in terms that are consistent in their general outlines with what the Antikythera mechanism does. Is the Antikythera mechanism the very device Cicero saw? We cannot know, but the coincidence of timing is suggestive, and the existence of the mechanism itself, regardless of who specifically made it, tells us something profound about the level of scientific and technical achievement in the ancient Greek world. The device represents a tradition of knowledge, of theoretical understanding, and practical craft that had taken centuries to develop. It was not a one-off miracle, a bolt of genius from a clear sky. It was the culmination of a long tradition, built on the work of generations of thinkers and makers who passed their knowledge down through teaching and demonstration and practice. And then it was lost, not suddenly, not in a single catastrophic moment, but gradually across the centuries of Roman domination. The decline of the great intellectual centers of the Greek world, the disruption of the trade networks that had brought scholars and craftsmen together, the slow fraying of the threads of transmission that had kept specialized knowledge alive. After the Antikythera mechanism, no comparable device appears in the historical record for more than 1,000 years. The next mechanical device of similar complexity we know of is the astronomical clock, built by Richard of Wallingford in England in the 1320s AUE, more than 13 centuries after the Antikythera mechanism sank to the seafloor. 13 centuries of silence. That silence is one of the most haunting things in the history of human knowledge. Something extraordinary was made, something was understood, and then, through the slow attrition of civilizational collapse and cultural disruption, it was simply forgotten. The gears stopped turning. The knowledge was not written down, or if it was, the writing did not survive. The craftsmen who could make such things had no apprentices who learned from them, or those apprentices had no apprentices of their own, and the tradition died. As you settle deeper into the night, hold that image for a moment. A small bronze device, turning silently in someone's hands 2,000 years ago. Its gears modeling the movements of the universe with perfect, patient precision. No electricity, no software, no factory-made parts, just bronze and mathematics, and the extraordinary capacity of the human mind to look at a complex and seemingly chaotic sky and find within it perfect order. Let us go to Egypt now. Let us go back further in time than the Antikythera mechanism. Much further, back to roughly 2560 BCE, which is the conventional dating for the construction of the Great Pyramid of Giza. Back 4,560 years to a world so distant from our own that the entire span of recorded European history fits comfortably within the time that separates us from it. Close your eyes and imagine the plateau at Giza as it would have looked in the years of construction, not the way it looks in photographs today. The pyramid standing alone in a dry urban landscape, tourist buses on the roads around them, a haze of Cairo's pollution on the horizon. Imagine it as it was, a broad limestone plateau above the floodplain of the Nile, alive with activity. Thousands of people moving across it in organized patterns, some pulling wooden sledges loaded with stone blocks, others setting mortar, others directing the placement of enormous pieces of limestone and granite with hand signals and ropes and levers. A vast, coordinated human enterprise spread across a space the size of a small city. And rising from the center of all this activity, already, even in its partially built state, the most monumental structure ever assembled by human hands. The Great Pyramid of Khufu is, even by modern standards, an astonishing feat of engineering. It contains approximately 2.3 million stone blocks. The average weight of these blocks is around 2.5 tons, with the largest, the granite blocks used in the king's chamber, deep inside the pyramid, weighing between 25 and 80 tons. The total mass of the structure is approximately 5.9 million tons. It covers an area of 53,000 square meters at its base and originally stood 146.5 meters tall, the tallest structure in the world for nearly 4,000 years, until the completion of the Lincoln Cathedral in England in 1311 CE. These are staggering numbers, but numbers alone don't capture what makes the Great Pyramid truly astonishing. What makes it truly astonishing is the precision. The base of the Great Pyramid is nearly a perfect square. The four sides of that square are each approximately 230 meters long. The maximum difference in length between the four sides is about 4.4 centimeters, an error of less than 0.02%. In a modern construction project with laser levels and GPS surveying equipment, this would be considered good work. In a construction project carried out 4,500 years ago, using rope and plumb bobs and sighting rods, and the unaided observation of stars, it is almost beyond comprehension. The base of the pyramid is level to within 2.1 centimeters across its entire 230-meter span. Again, laser-precise work, achieved 4 millennia before lasers existed. The sides of the pyramid are oriented to the cardinal directions, north, south, east, west, with an accuracy of within a fraction of a degree of arc. The north face deviates from true north by only 3 minutes and 6 seconds of arc. Consider what this means. In the ancient world, there was no compass. True north could only be determined by careful astronomical observation, watching the movement of circumpolar stars and finding the precise point around which they appeared to rotate. To orient a structure of this size to within 3 arc minutes of true north, across a construction period of decades, using only the stars for reference, is a navigational achievement that still draws admiration from modern surveyors and astronomers. The internal chambers and passages of the pyramid show the same extraordinary care. The Grand Gallery, a corbelled stone corridor that ascends at a steep angle through the pyramid's interior, is constructed with such precision that its walls are still, 4,000 years later, as smooth as they were when first assembled. The King's Chamber, built entirely of large granite blocks brought from Aswan, 600 miles to the south, is a room whose walls and floor and ceiling are aligned and finished to tolerances of fractions of a millimeter. How was all of this done? This is the question that has obsessed architects, engineers, archaeologists, and historians for centuries. And the honest answer is that while we have partial answers, the complete picture remains unclear. We know certain things with reasonable confidence. We know from archaeological evidence, including workers' graffiti found in hidden chambers inside the pyramid, that the pyramids were built by Egyptian workers, not by slaves, as the popular imagination has often suggested. The workers appear to have been organized into gangs with their own identities and a degree of institutional pride. The graffiti includes boastful names like Friends of Khufu and Drunkards of Menkaure. Excavations near the pyramid complex have revealed a workers' village with bakeries, breweries, fish processing facilities, and a medical facility. Evidence of a well-organized, well-fed workforce of skilled laborers who were provided for by the state. We know from surviving tools and depictions in tomb paintings and relief carvings that the Egyptians used copper chisels and drills for their stonework, wooden sledges for transport, ropes of twisted plant fiber for pulling loads, and an understanding of leverage and inclined planes for moving heavy weights. Experimental archaeology, building projects that attempt to replicate ancient techniques with ancient tools, has demonstrated that a surprisingly large amount of the pyramid's construction can, in theory, be accomplished with these relatively simple technologies, given a sufficiently large, well-organized workforce. But the theory runs into difficulties when you push it to its limits. The problem is not just the size of the blocks or the volume of the work. The problem is the precision. A wooden sledge on a lubricated track can move a 2.5-ton stone block with perhaps 50 men pulling. A large workforce can quarry and dress stone with copper tools. These things are demonstrable, but the geometric precision, the near-perfect squareness of the base, the alignment with the cardinal directions, the millimeter-level accuracy of the internal chambers, requires not just labor, but knowledge. Deep, sophisticated mathematical and astronomical knowledge, applied with extraordinary consistency across decades of construction. The Egyptians, we know, had a sophisticated understanding of practical geometry. The Rind Mathematical Papyrus, an ancient Egyptian document dating from around 1550 BCE, though probably copied from earlier sources, demonstrates a working knowledge of fractions, area calculations, volume calculations, and the use of what we would recognize as a form of coordinate geometry. But the Great Pyramid predates even this document by 1,000 years, which means the mathematical knowledge embedded in its construction was current by 2560 BCE and had been current for long enough to be practically applicable at enormous scale. There is one aspect of the pyramid's construction that many people don't know about, and which reveals something important about the intellectual world that produced them. The pyramids are not just large, they encode information. The ratio of the Great Pyramid's perimeter to its height is approximately 2 pi, the ratio you get when you calculate the circumference of a circle using its radius. Whether this is intentional or coincidental is debated, but the precision of the pyramid's dimensions makes pure coincidence seem unlikely. Some researchers have noted that the pyramid's slope angle of approximately 51.84 degrees is very close to the angle you would get if you rolled a circle of radius equal to the pyramid's height along a flat surface. The pyramid also appears to encode the distance from the Earth to the Sun in its proportions. The ratio of the pyramid's height to the perimeter of its base, multiplied by a factor of 43,200, gives a figure very close to the Earth's polar radius. Again, coincidence or deliberate encoding? The ancient Egyptians do not appear to have left written records explicitly saying, "We built this so that its proportions represent the Earth," and the absence of such records makes certainty impossible. What is certain is that the mathematical knowledge required to plan and execute this structure, to maintain its extraordinary precision across a construction project lasting perhaps 20 years, across a surface area of 5.5 hectares, far exceeds what most people intuitively expect of a Bronze Age civilization. This is the puzzle that makes the pyramids not just impressive, but genuinely mysterious. Not the size of the blocks, not the number of workers, but the precision, the knowledge, the mathematical sophistication embedded in every dimension, every angle, every perfectly fitted joint. And there are not just the pyramids at Giza. There are more than 100 pyramid sites in Egypt, spanning more than 1,000 years of construction. The tradition of pyramid building represents a sustained, evolving, institutionally transmitted body of engineering knowledge, of remarkable depth and continuity. Until it stopped. Until, like the Antikythera mechanism, the knowledge was lost. The last Egyptian pyramids, built in the New Kingdom period, are not as precisely or as durably constructed as the Old Kingdom giants. The quality declined over time, suggesting that the specific knowledge of how to build the great ones was gradually attenuating, that the transmission chain between the master builders and their successors was weakening, the traditions becoming more ritual than practical, the understanding of the underlying principles fading even as the form persisted. Eventually, no more pyramids were built. The knowledge of how the great ones had been built was gone, absorbed into the same darkness that swallowed so much of the ancient world. What remains is the stone, patient, precise, immovable, waiting for us to figure out what we're looking at. Let us shift from the scale of the pyramids to something smaller but no less remarkable. Let us talk about concrete. I know, concrete does not sound mysterious. Concrete is the ubiquitous, gray, slightly depressing material of parking garages and sidewalks and brutalist apartment buildings. Concrete is practical. Concrete is functional. Concrete is, in the popular imagination, about as far from mysterious as it is possible to get. But Roman concrete, opus caementicum, as the Romans called it, is something else entirely. And understanding why it is something else takes us deep into one of the most interesting unsolved materials, science puzzles of the modern era. Our modern concrete, Portland cement concrete, has a lifespan problem. Under normal conditions, exposed to weather, moisture, and the physical stresses of daily use, modern concrete begins to degrade after approximately 50 years. The degradation is gradual at first, then accelerating. Small cracks form, water penetrates them, and expands when it freezes. The steel reinforcing rods inside the concrete begin to rust as moisture reaches them, and the rust expands and forces the concrete apart from within. The breakdowns you see in infrastructure all around you, the cracked sidewalks, the spalling bridge decks, the deteriorating parking structures, are the result of this predictable, essentially unavoidable process. Roman concrete, on the other hand, has been sitting in the Mediterranean environment for 2,000 years, and in many cases is structurally sound. Some of it is in better condition now than it was a few centuries after it was poured. In the harbors of ancient Roman ports around the Mediterranean, at Caesarea Maritima in Israel, at Pozzuoli, on the Bay of Naples, at various sites around the coasts of Italy, France, and Spain, there are massive concrete structures that were poured underwater in the 1st century BCE and 1st century CE. These harbor walls, breakwaters, and foundations have been subjected to 2,000 years of wave action, saltwater penetration, chemical attack from the sea, biological activity from organisms that colonize marine structures, and the physical stress of enormous loads resting on them. They are stronger than when they were new. This is not a figure of speech. Researchers at the University of California, Berkeley, working with colleagues at several European institutions on a project funded by the United States Department of Energy, have analyzed samples of ancient Roman harbor concrete and found that the seawater has not degraded the material. It has caused it to grow new mineral crystals within its structure. The concrete has, over 2,000 years of immersion, been continuously reinforcing itself at the molecular level. The key to this self-reinforcement lies in the specific materials the Romans used in their concrete mix. Modern Portland cement concrete uses a calcium silicate hydrate binder, a material produced by heating limestone and clay to extremely high temperatures and then mixing the resulting powder with water. This binder is strong in compression, which is why concrete makes good foundations and columns, but it has a fundamental chemical incompatibility with salt water. The chloride ions in seawater attack the calcium silicate and gradually break it down. This is the core of the modern concrete durability problem. Roman concrete used a completely different binder, a mixture of seawater, lime, calcium hydroxide, and pozzolana, a volcanic ash found around the Bay of Naples and known to the Romans as pulvis pudiolanus, Puteolian dust, named for the Roman city of Puteoli. The Romans had discovered, through empirical observation and centuries of building experience, that this particular type of volcanic ash produced concrete of extraordinary durability when mixed in the right proportions. Vitruvius, the 1st century Roman architect and engineer, discusses the properties of pozzolana in his architectural treatise De Architectura, and notes its particular suitability for construction in or near the sea. What Vitruvius did not know, and what modern chemistry has now explained, is why the volcanic ash works so well. When seawater percolates through Roman concrete over long periods, it reacts with the aluminous tobermarite mineral structure that forms in the pozzolana-lime mixture and encourages the growth of a mineral called philipsite, a zeolite that forms long interlocking crystals within the concrete's pores. These crystals bind the concrete's components together more tightly than the original setting process did, effectively repairing and strengthening the material from within. The Romans did not understand this chemistry. They didn't need to. They had observed that Puteolian ash made excellent harbor concrete. They had recorded this observation in their engineering manuals, and they had applied it faithfully in harbor construction across the entire Mediterranean world. But here is the deeper mystery, the source of this knowledge. The use of pozzolanic ash in construction appears to predate the Romans. Evidence of pozzolanic concrete construction in the ancient Mediterranean world goes back at least to the 2nd century BCE, and possibly earlier. The knowledge of this technique, this very specific, very counterintuitive technique of mixing volcanic ash with lime and seawater to create underwater hardening concrete, appears to have developed gradually within the Roman engineering tradition, possibly based on earlier Greek or Italic building practices, and possibly informed by knowledge of earlier uses of similar materials in other Mediterranean cultures. The Romans were not scientists in the modern sense. They did not conduct controlled experiments or publish peer-reviewed papers, but they were brilliant empirical engineers, and their tradition of engineering knowledge was preserved and transmitted through a system of apprenticeship and accumulated experience that allowed genuinely significant innovations to be identified, refined, and disseminated across the entire Roman world. The tragedy, from a modern infrastructure standpoint, is that this knowledge was lost, along with the rest of Roman engineering tradition, when the Western Roman Empire collapsed in the 5th century CE. The sources of pozzolanic ash were not always accessible to medieval builders. The skilled engineers who understood how to identify and use it, and who knew the correct proportions of the mix, were not available. And perhaps most importantly, the institutional structures, the Roman army's engineering corps, the imperial public works departments, the tradition of technically sophisticated architectural treatises, like Vitruvius, that had preserved and transmitted the knowledge, were gone. Medieval builders in Western Europe reverted to simpler lime mortars that did not have the durability of Roman concrete. The great harbors began to deteriorate. New structures were not built to the same standard, and the specific technique, pozzolanic concrete mixed with seawater, was simply forgotten, lying dormant in the crumbling harbor walls of ancient ports, waiting for 21st century scientists to rediscover it. Modern materials scientists and civil engineers have spent the last decade intensively studying Roman concrete, hoping to incorporate its insights into new, more durable infrastructure materials. Progress has been made. Synthetic pozzolanic additives are now incorporated into some specialized modern concrete mixes, improving their durability and reducing their carbon footprint. But the specific Roman formulation, particularly for marine applications, remains technically difficult to reproduce at scale. The sea has had 2,000 years to test Roman concrete and has declared it adequate. 2,000 years. As you breathe slowly in the quiet of tonight, let that sit with you. The harbor walls at Caesarea Maritima, built when Augustus Caesar was reorganizing the Roman world and Cleopatra was within recent memory, are still standing in the Mediterranean Sea, being slowly made stronger by the very water that should be destroying them. There is a map in the Topkapi Palace Museum in Istanbul that has troubled historians since it was first brought to public attention in 1929. It is called the Piri Reis map, and it was drawn in 1513 CE by an Ottoman admiral named Piri Reis, who noted in an inscription on the map itself that he had compiled it from older source maps, some of them, he claimed, dating back to the time of Alexander the Great. The map shows the Atlantic Ocean, the coasts of Europe and Africa, and the western coast of the continent that Europeans at that time were just beginning to understand as the Americas. This much is explicable. By 1513, Columbus had made his famous voyages, and other explorers were actively mapping the New World's coastlines. But the southern portion of the Piri Reis map shows something that should not be there: a landmass south of the equator, connected to South America, with a coastline that bears a suspicious resemblance to Antarctica. Antarctica was not officially discovered until 1820, by which time the Piri Reis map was already 300 years old. The immediate objection is that the resemblance is coincidental, that any roughly east-west oriented landmass at the bottom of a map might superficially resemble Antarctica without actually representing it. This objection has merit, and the scholarly consensus is that the southern landmass on the Piri Reis map is most likely a depiction of a speculative terra australis incognita, the unknown southern continent that ancient and medieval cartographers placed on their maps to balance the known northern landmasses, based on theoretical geographical reasoning rather than actual observation. But the Piri Reis map is not the only anomalous ancient map. Far from it. Consider the Oronteus Finaeus map of 1531, which shows Antarctica as a continent largely free of ice, with river systems suggesting a temperate or subpolar climate, consistent with what Antarctica might have looked like before the last glacial advance covered it in ice, somewhere around 12,000 years ago. Consider the Boachi map of 1737, which shows Antarctica divided into two separate islands, a geographical feature that was confirmed by seismic surveys in the 20th century, but which would have been invisible under the continent's ice sheet to any observer in the 18th century or earlier. Consider, outside the Antarctic mystery entirely, the Vinland map, a map that supposedly dates from around 1440 CE and shows the North American coast above the Atlantic, including a large island labeled Vinland that is generally interpreted as representing the Norse settlements in Newfoundland, documented in the Icelandic sagas. The authenticity of the Vinland map is itself deeply disputed, but the concept it represents, pre-Columbian knowledge of a transatlantic landmass, is not as far-fetched as it once seemed, given the confirmed archaeological evidence of Norse settlement at L'Anse-aux Meadows in Newfoundland around 1000 CE. But the deepest and most ancient cartographic mysteries are not about modern-looking maps of unexpected places. They are about the mathematical sophistication embedded in ancient geographical knowledge. The ancient Greeks understood that the Earth was spherical. This is not a surprising claim. It has been known since at least the 6th century BCE, and Eratosthenes calculated the Earth's circumference with remarkable accuracy, within about 2% of the modern value. In the 3rd century BCE, using nothing more than the angle of shadows cast at different locations at the same time of day. But translating knowledge of the Earth's spherical shape into accurate flat maps requires mathematical techniques that most ancient civilizations are not supposed to have possessed. Yet ancient maps from multiple cultures, Greek, Roman, Arab, and Chinese, show a sophisticated understanding of latitude that goes beyond what you would expect from simple observation. Some show the use of a form of projection that correctly represents distances and directions across large areas of the Earth's surface. The Ptolemaic world map, compiled by the Alexandrian geographer Claudius Ptolemy in the 2nd century CE from older sources, is remarkable for its systematic use of coordinates and its explicit discussion of the mathematical problems involved in projecting a spherical surface onto a flat plane. Ptolemy's coordinate system, with parallels of latitude and meridians of longitude defined by astronomical observations, is intellectually continuous with the coordinate systems used in modern geography. His maps were not perfectly accurate. His distances in Asia and Africa were distorted by relying on travelers' estimates of travel times rather than astronomical observations, and he significantly underestimated the size of the globe, a mistake that would later give Columbus false confidence that he could reach Asia by sailing west. But his conceptual framework was modern in its essentials. The sources Ptolemy drew on went back centuries. He explicitly cites earlier geographers, including Marinos of Tyre, and, further back, figures whose works are now lost. The geographical tradition he represented was old and deep, a tradition of maritime navigators and explorers accumulating knowledge of the world's coasts and interiors over centuries, of mathematicians and astronomers working to reduce that knowledge to a systematic, geometrically rigorous form. That tradition included knowledge that has not always survived in recognizable form. In ancient Polynesian navigation, for example, the tradition that enabled the settlement of the Pacific Islands, the most remarkable feat of maritime exploration in human history, navigators read the ocean itself as a map. They felt the patterns of ocean swells and identified which island or archipelago was disturbing them from a distance. They read the behavior of stars near the horizon to determine latitude. They observed the behavior of birds, the temperature and color of the water, the patterns of phosphorescence in the night sea, the feel of the current against the hull of their canoe. This knowledge was not written down. It was not encoded in maps on vellum or papyrus. It was held in the body and mind of individual navigators, transmitted through years of apprenticeship and practice, expressed in star charts made of sticks and shells that encoded the swell patterns and star paths of vast oceanic routes. And much of it was lost. When the epidemics brought by European contact devastated Pacific Island populations in the 18th and 19th centuries, the master navigators died with their knowledge. The traditions of wayfinding that had enabled humans to settle every habitable island in the world's largest ocean, from Madagascar to Easter Island, from Hawaii to New Zealand, were almost entirely lost within a few generations. What remained were the islands themselves and the oral traditions and fragments of the stick charts preserved in museums, and the growing evidence of the archaeological record. The presence of Polynesian populations in places like the Hawaiian Islands and Aotearoa, New Zealand, that could only have been reached by people who knew exactly where they were going across thousands of miles of open ocean. The ancient world was mapped in every culture's own way. The knowledge of that mapping was vast and sophisticated, and in many crucial respects, irretrievably gone. What remains is the suggestion of it, the maps that survived, the anomalies within them, the glimpses of a geographical understanding, deeper and wider than we expected to find in the ancient world. As your eyes grow heavier and the night deepens around you, think of those Polynesian navigators on the open Pacific at night, stars wheeling overhead, the ocean breathing under the hull, no landmark anywhere for 1,000 miles in any direction, and the navigator knowing, with absolute certainty, exactly where home was. In 1938, a German archaeologist named Wilhelm Koenig, working in the collections of the National Museum of Iraq in Baghdad, found himself examining an unusual clay jar from the village of Kujut Rabu, near the ancient Parthian city of Ctesiphon. The jar was small, about 14 centimeters tall, roughly the size of a drinking glass, and had been found in a context dating from the Parthian period of Mesopotamian history, roughly 250 BCE to 224 CE. What Koenig found inside the jar was what prompted his attention. The jar contained a copper cylinder, crimped at the bottom, sealed at the top with asphalt. Inside the copper cylinder was an iron rod, also sealed in the asphalt stopper, and positioned so that it ran down the center of the copper cylinder without touching its walls. Koenig looked at this arrangement and experienced a flash of recognition. The configuration: an iron rod inside a copper cylinder, separated by a non-conducting material. The whole thing sitting in what would originally have been some kind of electrolytic liquid was, in its essential layout, a galvanic cell, a battery. He published his interpretation in 1940, and his paper sparked a debate that has never been fully resolved. The principle of the galvanic cell was formally described by the Italian physicist Alessandro Volta in 1800, when he invented the voltaic pile, the first true electrical battery. Volta's invention was based on the observation, first made by Luigi Galvani, that metals in contact with a saline solution could produce an electrical current. Volta stacked alternating discs of zinc and copper, separated by cloth, soaked in salt water, measured the electrical potential produced, and thereby launched the age of electrical technology. The Baghdad jar, if filled with an acidic or saline liquid, wine, vinegar, lemon juice, or a salt solution all work, and connected to a circuit by wires attached to the copper and iron electrodes, produces approximately 1.1 to 2 volts of electrical potential. This has been demonstrated experimentally, most famously by German Egyptologist Arne Eggebrecht in the 1970s, and by television productions testing the concept. The device functions as a battery. But, and this is the crucial but, does the fact that it functions as a battery mean that the Parthian people who made it knew it was a battery? This is the central question, and it is much harder to answer than the physics. The case against the ancient battery interpretation is straightforward. We have no textual evidence in any surviving Parthian, Mesopotamian, or any other ancient source of the use of electricity for any purpose. We have no other electrical devices from the ancient world. We have no evidence of any technology that would require a source of electrical current to function. The Baghdad battery is a single object, or rather a handful of similar objects found in the same general region and time period, without any supporting context that would explain what it was used for, or whether its electrical properties were intentionally designed. The case for the ancient battery interpretation is more circumstantial, but not entirely without force. The specific configuration of materials, iron inside copper, is not a coincidence you would arrive at by accident if you were making a storage jar. Iron rods inside copper cylinders is not a natural or obvious way to store anything, and the configuration is precisely what you would design if you wanted a galvanic cell. The asphalt seal preserves the geometry of the internal electrodes, suggesting that their precise positioning relative to each other was important, and the fact that multiple similar devices have been found in the same region and period suggests a manufacturing tradition, not an accidental combination. What might ancient people have used small amounts of electrical current for, if they had it? Eggebrecht, who tested the Baghdad battery in the 1970s, suggested electroplating, the process of using electrical current to deposit a thin layer of one metal onto the surface of another. He demonstrated that the battery's current was sufficient to electroplate a silver figurine with a thin layer of gold. And some archaeological objects from the region and period do show metal coatings that have puzzled metallurgists, since the thinness and evenness of the coatings are not easily achieved by the gilding techniques that were otherwise known in the ancient world. The electroplating theory is intriguing, but not proven. And there are other possibilities. Pain relief through electrical stimulation was a medical practice in the ancient world, though using electric eels, not batteries. Some researchers have suggested ritual or religious uses for a device that could produce tingling or numbness. The ancient world had many uses for unusual sensory phenomena that we would not necessarily anticipate. What the Baghdad battery controversy ultimately illustrates, regardless of what it actually was, is the danger of assuming that the boundaries of ancient knowledge were where we expect them to be. The history of science and technology has been consistently humbled by the discovery that capabilities and knowledge we assumed were modern achievements turn out to have been anticipated in some form. In earlier eras and different cultures, ancient people were not less intelligent than we are. Their brains were the same size, their capacity for curiosity and observation and creative problem-solving was the same as ours. What they lacked was accumulated institutional knowledge the vast library of documented discoveries and methods that modern science builds on. But that deficit in accumulated knowledge did not prevent individual thinkers and craftsmen from making remarkable observations and developing remarkable capabilities from first principles through patient empirical work. The Baghdad battery may be exactly what it looks like, an ancient battery used for purposes we haven't fully determined, by people who had discovered the principles of galvanism 1800 years before Volta formally described them. Or it may be something else entirely, a storage vessel whose incidental electrical properties were never noticed by its makers. In either case, it sits in its museum case and asks its quiet question, what did you know? What did you discover in your patient, brilliant, pre-industrial way that the record of history has lost? The question does not demand an answer tonight. It only asks to be heard. Let us talk about something that burned. For more than 300 years, the Byzantine Empire, the Eastern Roman Empire, that survived the fall of Rome and preserved Roman-Greek civilization in Constantinople through the medieval period, possessed a military weapon of such devastating effectiveness that its very existence changed the balance of power in the medieval Mediterranean world. It was called Greek fire, and it was, in the words of historians who have studied it, one of the most psychologically devastating weapons in the history of warfare, not just because of the damage it caused, but because of what it seemed to be, a fire that burned on water, a fire that could not be put out, a fire that appeared, to those who saw it for the first time, to be something beyond the natural order of things. The first recorded use of Greek fire in battle was in 672 CE, during an Arab naval siege of Constantinople. The Arab fleet, which had superior numbers and was attempting to blockade the Byzantine capital by sea, was attacked by Byzantine warships armed with siphons, pressurized tubes that projected streams of burning liquid onto the Arab ships. The liquid ignited on contact with air and burned with terrifying intensity on the surface of the water. It could not be extinguished with water. It could not be smothered. It clung to wood and rope and cloth and human flesh and continued to burn. Sailors who jumped into the sea to escape the fire found that it burned on the water's surface, cutting off escape. The Arab fleet was destroyed. Over the following 3.5 centuries, Greek fire was used repeatedly to defend Constantinople from naval assault, most notably against the Arab besieging fleets of the 670s, 710s, and 718 CE, and against the Russian fleets that attacked Constantinople in 941 and 970 CE. The Rusi Prince Igor, whose fleet of reportedly several hundred ships attacked Constantinople in 941, described what happened to his fleet after encountering Byzantine fireships in terms that make clear the psychological impact of the weapon. The Greeks have something like lightning in the heavens, he reportedly told his people, and, releasing it, they burned our ships. The Byzantine Emperor Constantine VII, Porphyrogenitos, writing in the mid-10th century, described Greek fire as a divine gift to the founder of his dynasty, revealed by an angel, and strictly forbidden to be shared with any foreign power or ally. This description, part theological legitimation, part state secret classification, suggests the extraordinary importance the Byzantines placed on maintaining their monopoly over the weapon, and they maintained it remarkably well. Greek fire remained exclusively Byzantine for its entire period of use. Unlike most military technologies, it was not captured, reverse-engineered, or independently developed by Byzantine enemies during 3 centuries of being used against them. This itself suggests that the substance was genuinely difficult to understand and replicate. that it was not something that could be analyzed by recovering a sample and working backward to its composition. And then, in the 12th century, Greek fire disappears from the historical record. The last credible use of something identifiable as Greek fire was during the Byzantine defense against the Normans in southern Italy in the 11th century. After that, Byzantine sources stopped mentioning it. When the Crusaders sacked Constantinople in 1204, they found no Greek fire. When the Ottoman Turks finally captured Constantinople in 1453, bringing the Byzantine Empire to its end, there was no Greek fire. The secret had been lost. What exactly was Greek fire? This is one of the most actively debated questions in the history of technology, and it remains genuinely unresolved. Modern chemists and historians have proposed many possible formulations, and the true answer likely incorporates elements of several. The most credible theories involve naphtha, a naturally occurring petroleum product found in the Middle East, known in the ancient world, and used for various purposes, including in the eternal fires that burned at Zoroastrian temples in Persia. Naphtha is highly flammable, floats on water, and burns with a hot, persistent flame. Combined with quicklime, which reacts with water and generates heat, naphtha would ignite on contact with a wet surface, explaining Greek fire's ability to burn on water. The addition of natural resins and thickening agents would give the mixture the clinging, adhesive quality that ancient sources describe. The Byzantine innovation was likely not a single special ingredient, but rather the combination of ingredients and the delivery system. The pressurized siphons that projected the burning liquid under pressure, essentially functioning as ancient flamethrowers, potentially with a firing range of 20 or 30 meters. The combination of an incendiary liquid formulation with an effective mechanical delivery system created a weapons platform whose effectiveness was the product of both chemistry and engineering. But the specifics remain unknown because the Byzantines kept them unknown. They did not write down the full recipe. Or if they did, the documentation has not survived. The knowledge was held in the heads of a small group of specialists, the keepers of the secret, and transmitted orally and practically through direct instruction. When the empire weakened, when the population of Constantinople was decimated by plague and war, when the economic and political disruptions of the medieval period interrupted the chain of transmission, the specialists died, and the knowledge died with them. Greek fire is a perfect illustration of the fragility of highly specialized, deliberately protected knowledge. The very secrecy that gave it its military value also made it vulnerable to loss. If you never write something down, if you never transmit it more widely than a small circle of trusted craftsmen, then the destruction of that small circle destroys the knowledge itself. And Byzantine Constantinople, for all its extraordinary cultural resilience, it survived where Rome fell, preserving and transmitting the intellectual heritage of the ancient world for nearly 1,000 years after the fall of the West, was not immune to this kind of loss. The fires that burned on water burned for the last time, in some unnamed battle, in some unnamed year, and then they did not burn again. And the formula returned to silence. There are swords that have stood the test of centuries, and swords that have been forgotten. And then there is Damascus steel, which managed to do both simultaneously. From approximately the 3rd century CE through the early 18th century, swords made in the Islamic world from a material called wood steel, a high-carbon steel produced in crucibles in India and Sri Lanka, worked in Damascus and other centers of the Near Eastern arms trade, were renowned across the known world for qualities that were considered almost supernatural. They were sharper than any other blade. They were flexible enough not to shatter under impact. They held their edge through repeated use in a way that European steel of the period could not match, and they were covered in a distinctive surface pattern. flowing, wavy bands of light and dark running through the metal, like flowing water or wood grain, that made them immediately recognizable and deeply beautiful. Crusader knights who encountered Damascus steel blades in battle came home with stories of swords that could split a floating silk scarf and then cut through a European sword blade without dulling. These stories were probably somewhat embellished, as soldiers' stories tend to be, but they were rooted in a real difference in performance. Damascus steel blades were genuinely superior to contemporary European steel in several measurable respects, and European sword makers spent centuries trying to understand and replicate the quality. They were never quite able to. The modern European sword-making tradition, which used different methods of steel production and did not have access to the specific Indian wood steel that was the raw material for Damascus blades, could not reproduce the distinctive combination of sharpness, toughness, and pattern. European smiths who acquired Damascus blades and tried to reverse engineer the process from the finished product were working backward from an effect they could observe to a cause they could not see, the specific microstructure of the metal that produced the observed properties. And then, in the early 18th century, the production of Damascus steel stopped. The reasons are not entirely clear. The most commonly cited explanation involves the disruption of the trade routes that brought Indian wood steel to the Near Eastern smiths who worked it into finished blades. The specific ore deposits in southern India that produced the iron with the right trace element composition, including small amounts of vanadium, tungsten, and molybdenum that play crucial roles in the steel's microstructure, were reportedly exhausted or abandoned. Without the specific raw material, the specific process could not be applied, and the specific process, carried out by master smiths who understood their craft through practice rather than metallurgical theory, was not something that could simply be adapted to a different raw material. The combination of raw material supply disruption and the loss of the specific craft knowledge. When the demand dried up, the master smiths did not transmit their knowledge to a new generation, ended the tradition. Modern metallurgists and materials scientists have spent more than 2 centuries trying to rediscover the secret of Damascus steel, and they have made significant progress. Researchers in the 1970s and 1980s, using electron microscopy and chemical analysis of historical blades, determined that the surface pattern, the flowing bands of light and dark, is produced by a microstructure called carbide banding, in which particles of iron carbide, cementite, are distributed in a regular layered pattern through a matrix of pure iron. This layering gives the steel its combination of hardness from the carbide particles and toughness from the pure iron matrix. Even more remarkably, a 2006 study by researchers in Germany found evidence of carbon nanotubes, cylindrical structures of carbon atoms, a nanometer in diameter, one of the most exotic materials in modern nanotechnology, in the microstructure of a Damascus steel blade. If confirmed, this would mean that medieval smiths in the Islamic world were producing carbon nanotube reinforced steel 1,000 years before carbon nanotubes were discovered by modern science. The researchers were careful to note that the nanotube formation was almost certainly unintentional, an incidental product of the specific temperature and chemical conditions of the wood steel smelting process, not something the smiths understood or deliberately engineered. But the incidental product was still a nanostructure of extraordinary complexity and performance. The smiths did not know why their process worked. They knew only that it worked, and they knew how to make it work, and they knew how to recognize when it was working and when it was not. This knowledge, deeply embodied, experiential, practical, was sufficient for centuries of production of a material that modern science is only now beginning to fully understand. When the conditions that sustained the practice disappeared, The practice disappeared with them. The nanotubes remained, locked in museum blades, waiting for an electron microscope. In the high desert of southern Peru, on a plateau between the towns of Nazca and Palpa, there are drawings. They are very large drawings. Some of them are several hundred meters long. Some cover areas of several square kilometers. They depict animals: a hummingbird, a spider, a monkey, a condor, a whale, a dog, with a stylistic simplicity and geometric precision that is striking both in its beauty and in its scale. Others are purely geometric, straight lines extending for kilometers across the desert floor, without deviation. Trapezoids, covering areas large enough to land a small aircraft on, spirals and zigzags. The Nazca lines were created by removing the reddish-brown iron oxide-coated pebbles that cover the surface of the Nazca Plateau, revealing the pale yellowish ground underneath. The contrast between the removed pebble surface and the exposed ground creates the visible lines. The removed pebbles were piled along the edges of the lines, creating low borders that in some cases remain visible today. The figures can only be fully appreciated from the air. This last point has generated enormous amounts of speculation, and it is worth addressing directly. The lines were not made to be seen from the air. This is a misconception born of the fact that they were first brought to wide attention when commercial aircraft began flying over the plateau in the 1930s, and pilots noticed them. The figures are large, but they are also visible from the elevated terrain surrounding the plateau. From the hills at the edges of the desert plain, the largest figures are clearly visible in outline. The Nazca people almost certainly had no aircraft, and the lines were not intended for aerial viewing. What were they intended for? This remains one of the genuine archaeological mysteries of South America. The Nazca culture, which flourished in the region between approximately 100 BCE and 800 CE, did not leave written records that could explain the purpose of the lines. Archaeological evidence, including pottery and textiles, found in association with the lines and nearby ceremonial sites, provides cultural context, but not explicit explanation. The most widely accepted scholarly interpretation is that the lines were related to water and fertility rites. The Nazca Plateau is an extremely arid environment. Annual rainfall is minimal, and agriculture in the region depended on underground aquifer systems and to carefully manage the irrigation canals. Several of the straight lines appear to point toward or connect water sources. The animal figures: the hummingbird, which is associated in Andean cosmology with rain; the spider, whose behavior some Andean people used as a predictor of weather; the monkey, associated with the Amazon, and therefore with water, may have had ritual significance related to the agricultural calendar and the invocation of rain and fertility. What makes the Nazca lines remarkable from a technological standpoint, and what earns them a place in any discussion of ancient capabilities, is the geometric precision of their construction. The straight lines are extraordinarily straight. Measured against modern surveying standards, some of the Nazca lines extending for hundreds of meters show a deviation from straight of less than a meter across their entire length. This precision was achieved without any apparent surveying equipment, beyond ropes, stakes, and the basic principles of geometry. Experimental recreations of Nazca line construction by archaeologists and engineers have demonstrated that the straight lines can be reproduced using only wooden stakes and ropes. By establishing a baseline with a rope, then extending the line segment by segment, using the same alignment principle repeatedly. The technique is not complicated in principle, but its consistent application across large distances in the featureless desert environment requires discipline and careful attention. The animal figures, which are drawn as continuous single lines, with each figure completed without lifting the pen, as if drawn in a single continuous stroke, suggest a design process that was planned in advance and translated from a small sketch to a large desert canvas using scaling techniques. One proposed method involves drawing the design on a small grid and then transferring it to the desert using proportional scaling of the grid, a method used in many other ancient artistic traditions and demonstrably achievable with simple tools. The precision is impressive, but explicable through careful application of basic geometry. What is perhaps more remarkable is the sustained commitment to the project. The Nazca lines were created over a period of several hundred years, suggesting multiple generations of people maintaining the tradition of line making, the ritual or practical purpose of which was presumably transmitted along with the technical method. And then, as with so many ancient traditions, the Nazca culture declined, probably as a result of ecological disruption, including severe deforestation that destabilized the region's agricultural systems and water management, and the tradition of line making died with it. The lines remained. They remain today, preserved by the extreme aridity of the Nazca Plateau, in a condition that allows us to see them almost as they were when they were made. Ancient footsteps are still visible in the desert dust, ancient stake holes still present along the borders of the lines. A tradition of practice committed with such patient care to the surface of the earth that it outlasted its makers by 2,000 years. India is perhaps the civilization most consistently underestimated in popular histories of ancient technology, and it is worth spending time there. The textual record of ancient Indian science and technology is extraordinarily rich, richer than almost anywhere else in the ancient world, because the Brahmanical and Buddhist traditions of India preserved ancient texts with remarkable care and continuity. The Vedas, the oldest surviving text of any Indo-European language, were transmitted orally for millennia with a precision achieved through elaborate mnemonic and phonetic systems that preserved not just the meaning, but the exact pronunciation of every syllable. This tradition of precise textual transmission meant that technical knowledge recorded in Sanskrit texts had a reasonable chance of surviving across centuries in legible form. What those texts reveal about ancient Indian science and technology is in many cases genuinely astonishing. Let us begin with medicine. The Sushruta Samhita, a Sanskrit medical text whose core content is attributed to the physician Sushruta, and which was compiled in its current form roughly between 600 BCE and 600 CE, though its core content is generally dated to around 600 BCE, contains descriptions of surgical techniques that are, in their conceptual sophistication, not far from modern surgical practice. Sushruta describes over 300 surgical procedures and over 120 surgical instruments made of metal and other materials. He classifies wounds, discusses the healing of fractures, describes the removal of foreign objects from the body, and provides detailed instructions for operations, including the removal of cataracts from the eye, abdominal surgery, and the treatment of intestinal obstructions. But the most remarkable surgical innovation attributed to Sushruta is rhinoplasty, the reconstruction of the nose using a flap of skin taken from the forehead or cheek. This procedure, the Indian method of rhinoplasty, as it came to be known in European medical literature, was described by Sushruta in considerable detail, including the preparation of the forehead flap, the shaping of the new nose over a reed framework, and the aftercare of the surgical site. The procedure was not merely theoretical. It was practiced. When European travelers and soldiers in India in the 18th century observed Indian physicians performing nasal reconstruction, notably in a case documented in 1794 in the Gentleman's Magazine in London, they were observing a continuous surgical tradition that had been maintained through generations of medical apprenticeship for more than 2,000 years. The 1794 case report, describing the reconstruction of a nose that had been amputated as a punishment, is considered a landmark in the history of plastic surgery because it brought the ancient Indian technique to European medical attention and directly inspired the development of modern reconstructive surgery, a surgical technique continuously practiced for 2 millennia, was essentially unknown to European medicine until the 18th century. Sushruta also describes, in a passage that has attracted considerable attention from modern medical historians, the practice of what appears to be inoculation against smallpox. The passage describes taking material from a smallpox pustule, making a small incision in the arm of a patient to be protected, and introducing the pustule material into the incision, a procedure essentially identical to variolation, the precursor to vaccination that Edward Jenner discovered in 1796. The antiquity and authenticity of this passage in the Sushruta Samhita is debated by scholars, but if it accurately represents ancient Indian practice, it represents the recognition of the principle of acquired immunity 2,000 years before it was discovered in the West. Beyond medicine, ancient India gave the world, through mathematical and astronomical traditions that developed in the first millennium CE, the decimal place value number system, including the concept of zero as a number in its own right. This sounds abstract, but its technological implications are enormous. The Indian system of numeration, transmitted to Europe through Arab intermediaries and known today as the Hindu-Arabic numeral system, is the foundation of all modern mathematics and therefore of all modern technology. Without place value notation, arithmetic becomes enormously laborious. Try multiplying MC6XL7 by CDXC3 in Roman numerals, and you will immediately grasp the problem. The ancient Romans, for all their engineering genius, had a numerical system that made complex calculation extremely difficult, which is part of why they did not develop the kind of analytical mathematics that underlies modern science and engineering. The Indian mathematicians who developed the place value system, and particularly the concept of zero, the Brahmi script 0, appears in an inscription at the Chaturbhuj temple in Gwalior, dated 876 CE. Though the mathematical concept of zero as a number was being discussed in Indian texts considerably earlier, gave humanity a cognitive tool whose consequences are still unfolding. India also gives us, in this same period, the earliest developments of trigonometry in the form recognizable to modern students. The Aryabhatiya, written by the mathematician and astronomer Aryabhata in 499 CE, contains the first known table of sine values and develops a sophisticated system of spherical astronomy, the geometry of astronomical positions on the celestial sphere, that would deeply influence Islamic astronomy, and through it, the development of European astronomy and navigation. All of this, the surgery, the inoculation, the mathematics, the astronomy, was produced by a civilization with sophisticated institutional structures for preserving and transmitting knowledge. The Gurukul system of residential apprenticeship, the monastic universities like Nalanda and Takshashila, the elaborate tradition of commentary and sub-commentary on foundational texts that allowed each generation to add its insights to the accumulated wisdom of previous ones. Nalanda University, founded around the 5th century CE in what is now Bihar, in northeastern India, was at its height arguably the world's greatest center of learning, with a library that reportedly took several months to burn when the university was destroyed by the Ghurid invasion in 1193 CE. Up to 10,000 students lived and studied there at one time from across Asia, studying philosophy, logic, medicine, grammar. astronomy, and mathematics in a curriculum of extraordinary breadth and rigor. When Nalanda burned, a significant portion of the accumulated written knowledge of the Indian intellectual tradition burned with it. Not all. The tradition continued in other centers, and many texts survived. But the destruction of the library and the disruption of the institutional tradition represented a genuine and irreversible loss. Knowledge, even knowledge inscribed in books, is not perfectly durable. The books can burn, and the knowledge that lives only in books, without the living tradition of practice that gives it context and applicability, can become uninterpretable, even if the books survive. Let us go further back, much further back, into the deep prehistory of Europe, before writing, before metallurgy, in most of the continent, before the great civilizations of Egypt and Mesopotamia had reached their classical height, to the British Isles, roughly 5,000 years ago. The Neolithic and early Bronze Age peoples of northwestern Europe, a series of cultures whose names we have given them through archaeological reconstruction: Windmill Hill culture, Beaker culture, Wessex culture, but whose own names for themselves we will never know, built monuments of a scale and precision that, like the pyramids of Egypt, consistently astonish modern engineers who study them carefully. Stonehenge is the most famous of these monuments, but it is emphatically not unique. The British Isles and coastal Atlantic Europe are covered, literally covered, with over 35,000 surviving examples. In megalithic structures, stone circles, passage tombs, standing stones, stone avenues, long barrows, and other configurations whose functions range from the astronomically sophisticated to the entirely unclear. Stonehenge is simply the most elaborate, the most carefully studied, and the most photogenic of a tradition of stone building that stretched from the Orkney Islands off the northern coast of Scotland to the Algarve coast of Portugal, spanning more than 3,000 years of continuous practice. What makes Stonehenge genuinely remarkable from a technological standpoint is not the size of its stones, though some of the sarsen uprights weigh over 25 tons, but the precision of their arrangement and the distance from which some of them were transported. The blue stones of Stonehenge, the smaller inner circle, whose stones are a distinctive blue-gray, spotted dolerite, were quarried in the Preseli Hills of West Wales, approximately 240 kilometers from Stonehenge as the crow flies, and considerably further by any practical land route. Moving stones weighing between 2 and 5 tons, a distance of 240 kilometers, using only Neolithic technology, wooden sleds, ropes of plant fiber, human muscle power, and possibly wooden rollers and waterborne transport, is an engineering challenge of the first order. It is not impossible. Experimental archaeology has demonstrated workable methods, but it requires coordination, planning, and sustained effort across many generations. The sarsen stones, the larger, more imposing outer circle, and the famous trilithons, pairs of uprights capped by horizontal lintels, came from Marlborough Downs, about 30 kilometers to the north of Stonehenge. Each sarsen stone was shaped at the quarry site by a process of pounding with other stones to remove rough protrusions, then finished to a relatively smooth surface. The lintels of the outer circle are curved in their horizontal dimension to follow the line of the circle, and their ends are connected by a mortise and tenon joint, a carpentry joint made in stone that locks each lintel to its uprights with a vertical peg fitting into a corresponding socket. Mortise and tenon joints in stone. At Stonehenge, the people who built Stonehenge were working in a material whose properties are very different from wood, and they were applying to it techniques normally associated with woodworking. A transfer of technology between materials that requires both an understanding of structural principles and a willingness to innovate. The result is a structure whose surviving stones are still standing and still connected 5,000 years after they were raised. The astronomical orientation of Stonehenge has been known since at least the 18th century. The monument is precisely aligned so that the midsummer sunrise, on the longest day of the year, occurs directly over the heel stone, as seen from the center of the stone circle. The midwinter sunset, on the shortest day of the year, occurs in the exactly opposite direction, and a growing evidence from detailed astronomical analysis suggests that Stonehenge may have encoded alignments to the Moon's complex 18.6-year cycle, as well as to solar events. The analysis of the spacing and positioning of various stone and post holes around the monument suggests a sophisticated understanding of the metonic and other astronomical cycles. These are people without writing, without metal tools, without wheeled vehicles in the conventional sense, without any of the standard markers of civilization as traditionally defined. And they were tracking the motions of the sun and moon with sufficient precision to align a monument of 25-ton stones to within fractions of a degree of astronomical events that occur once a year. The knowledge required to do this, to observe and record astronomical events over many years, to identify the precise direction of solstice sunrise and moonrise, to translate that direction into the orientation of a large construction project with appropriate accuracy, is not trivial. It required patient, systematic observation over many years, the ability to transmit the results of that observation to the next generation, and the ability to apply them practically in a construction context. This knowledge was built up, stone by stone and year by year, within an oral tradition that left no written record. We can infer it from the monuments, but we cannot read it from any surviving text. When the megalithic tradition ended, as it did gradually, in the Bronze Age transition, as the societies that had built the monuments were transformed by the arrival of metallurgy, new agricultural practices, and possibly new population groups, the knowledge of why and how the monuments had been built faded with the tradition. We are left with the stones, patient, enormous, precisely placed, waiting in the Wiltshire rain, as they have been waiting for 5,000 years, for us to fully understand what they are trying to tell us. Let us stop for a moment in the middle of our journey through the ancient world's technologies and talk about loss itself. There is no single symbol of lost knowledge more resonant, more frequently invoked, more emotionally powerful than the Library of Alexandria. It has become, in the cultural imagination of the modern world, the great symbol of what could have been, the repository of all human knowledge destroyed by fire, and with it the possibility of a different, more scientifically advanced history. The reality of the Library of Alexandria is more complicated and ultimately even sadder than the simple story of a single catastrophic burning. The Royal Library at Alexandria, founded under Ptolemy I Soter, or Ptolemy II Philadelphus, probably in the early 3rd century BCE, as part of the intellectual complex associated with the Museum, was from its beginning an institution with an explicitly totalizing ambition. The Ptolemaic kings wanted to collect, as one ancient source puts it, all the books in the world. Royal ships docking at Alexandria were reportedly required to surrender any books on board for copying, receiving the copy while the original was retained by the library. Ptolemaic agents traveled throughout the Mediterranean world, acquiring texts by purchase or by other means. The library's first chief librarian, Zenodotus of Ephesus, undertook the systematic collection and editing of the Homeric epics. His successors produced the definitive scholarly editions of virtually every major Greek author. At its height, the library reportedly held somewhere between 400,000 and 700,000 scrolls, not books in the modern sense, but papyrus rolls, each containing a work, or a portion of a work of ancient literature, science, philosophy, drama, history, mathematics, medicine, or geography. The scope was not merely Greek. The library collected texts in Aramaic, Hebrew, Egyptian, Persian, and other languages, some of which were translated into Greek for wider access. The Royal Library was accompanied by a daughter library in the Serapeum Temple complex, which housed an overflow collection and was more publicly accessible. The Museum, the research institution whose scholars lived in residence and whose salaries and expenses were paid by the crown, was the intellectual heart of the complex, the space where the world's greatest minds worked, debated, collaborated, and produced new knowledge, sustained by royal patronage and surrounded by the world's largest collection of existing knowledge. What happened to it? This is where the simple story of "it burned" breaks down. The library's destruction was not a single event. It was a slow attrition, a gradual diminishment over several centuries, punctuated by specific acts of destruction, until the institution and the collection were gone. Julius Caesar's forces accidentally burned a portion of the waterfront in Alexandria during his military campaign there in 48 BCE, and ancient sources suggest that this fire destroyed some portion of the library's collection, though the extent of the damage is debated, and some sources suggest that what burned was a collection of books awaiting shipment rather than the library itself. Caesar is also sometimes credited with beginning the process of rebuilding the collection by authorizing the transfer of the library of Pergamon to Alexandria. The Christian bishop Theophilus oversaw the destruction of the Serapeum complex in 391 CE, including whatever portion of the library's collection was housed there. The Muslim-Arab conquest of Egypt in 642 CE has been associated, in some medieval sources, with the destruction of the library, though this account is almost certainly a later invention. The library, in any meaningful sense, appears to have ceased to exist long before the Arab conquest. The more accurate picture is this. The library declined gradually over several centuries as the political and economic conditions that had sustained it were undermined. The Ptolemaic patronage that had funded it ended when Rome absorbed Egypt in 30 BCE. Roman support for Alexandrian scholarship was more intermittent and less lavish. The physical city of Alexandria experienced significant violence and disruption in the 2nd and 3rd centuries AD. Riots, military campaigns, sectarian conflicts. The papyrus scrolls that constituted the collection required constant maintenance and replacement as they decayed. Without sustained institutional support and effort, the collection would slowly deteriorate. Specific acts of destruction accelerated the decline, but the slow drain of neglect and disruption was probably more significant in the long run. What was lost? We can answer this question partially, because we know from ancient literary references that certain texts existed and were housed in Alexandria that are now entirely gone. The complete works of hundreds of ancient Greek authors, tragedies, comedies, historical works, philosophical treatises, scientific texts, are known only through fragmentary quotations in works that survived. Euclid's full original works survive only in medieval copies. We do not know how much of what Euclid actually wrote has been lost. Apollonius of Rhodes wrote a great poem of which we have only part. Eratosthenes' geographical works survive only in summaries and quotations. Aristarchus of Samos, who proposed that the Earth orbits the Sun 17 centuries before Copernicus, left works that are now lost. We know of his heliocentric theory only because other writers mentioned it. What we do not know is what we don't know we've lost. The texts we know are gone are those that survived long enough in some form for later writers to reference them. The texts that were lost entirely, before anyone thought to make note of their existence, are by definition unknown to us. The Greek mathematician Hero of Alexandria, who lived in the 1st century CE, is known from surviving works to have designed a steam-powered device, essentially a primitive steam turbine, in which steam escaping from a rotating ball through nozzles caused it to spin. Did he, or other ancient engineers, extend this concept further? Did the ancient world develop steam power beyond this demonstration device in forms that were never widely adopted and whose records were lost? We cannot know. The Library of Alexandria is a wound in the history of human knowledge, not because of the melodrama of its destruction, fires and iconoclasts and barbarian invasions, but because of the quieter, more pervasive reality it represents, that the accumulated knowledge of any civilization is fragile, that transmission is not automatic, that the chain from one generation to the next requires constant maintenance, constant effort, constant institutional investment, and that when the conditions sustaining that chain are disrupted, by war, by poverty, by the collapse of the political structures that funded the institutions, by epidemic, by ecological crisis, the knowledge in the chain does not float free and survive on its own. It sinks. It goes dark. The Romans built an empire on infrastructure, not only on armies and laws and political structures, though they had all of those in formidable measure, but on the physical infrastructure that connected the empire, supplied its cities, and maintained the conditions of stable, prosperous daily life across a territory stretching from Scotland to Mesopotamia. The Roman road system, at its height, comprised approximately 85,000 kilometers of roads, enough to circle the earth twice. These were not dirt paths or rough tracks. They were engineered structures, built in layers, designed to last and to carry heavy military and commercial traffic in all weather conditions. The typical Roman road was constructed on a foundation of large flat stones, covered by a layer of crushed rock and gravel, topped by a surface of stone slabs, fitted together with a slight crown, a convex profile, across the road's width, to shed rainwater. The roads were typically elevated slightly above the surrounding terrain to aid drainage, and drainage ditches ran along their sides. Milestones marked distances and provided navigation information. The quality of Roman roads was such that many of them are still visible, still in use as the foundations of modern highways, still structurally sound 2,000 years after construction. The Appian Way, the Via Appia, built beginning in 312 BCE to connect Rome with southern Italy, can still be walked on original Roman paving stones near Rome. Sections of Roman road in Britain, buried under subsequent road surfaces, are regularly uncovered by road maintenance projects and found to be in better condition than the more recent surfaces above them. But roads, impressive as they are, may not be the most extraordinary Roman engineering achievement. That distinction may belong to the aqueducts. The Roman city of Rome, at the height of the empire, in the 2nd century CE, had a population of somewhere between 1 and 1.5 million people. By far the largest city in the Western world, and one of the largest cities in the world at that time. Feeding, supplying, and providing water to a city of this size, in an age before pumps, before pipelines, before municipal water systems of any kind, was a challenge of staggering proportions. The Romans solved the water problem with 11 aqueducts, bringing fresh spring water from sources up to 90 kilometers away, in the hills surrounding the city. The longest, the Aqua Anio Novus, stretched nearly 90 kilometers. Together, the 11 aqueducts delivered approximately 1 million cubic meters of water to Rome every day, roughly 1 cubic meter per person, which is comparable to modern per capita water consumption in developed cities. The engineering principle of the aqueduct is simple. Water flows downhill. An aqueduct is nothing more than a gently inclined channel designed to carry water from a higher source to a lower destination by gravity alone. But maintaining a gentle and consistent gradient over long distances, over variable terrain, across valleys and through hills, is an engineering challenge that requires precise surveying, meticulous planning, and the ability to build structures, bridges carrying the water channel across valleys, tunnels carrying it through hills, of high precision and durability. The Pont du Gard, a Roman aqueduct bridge in southern France, built in the 1st century CE, is 50 meters tall and 3 tiers high. Its arches maintain the gentle 1 in 3,000 gradient required for water flow across a valley 275 meters wide. The foundation stones of its arches weigh over 6 tons each and were fitted without mortar, locked in place by gravity and the precision of their cutting. It has stood for 2,000 years without any restoration work, and it still works. Water still flows through the channel at the top. When tested, the water delivered by the aqueducts went to a vast system of fountains, public baths, private houses, and the enormous quantities of water required by the city's industries and its hundreds of public latrines. The latrine at Ostia, Rome's port city, accommodates 20 seats in a single room, arranged around a channel of continuously flowing water, a practical engineering solution to sanitation at scale that would not be seen again in Europe until the 19th century. When the Western Roman Empire collapsed in the 5th century CE, the aqueducts fell into disrepair within a generation or two. Without the institutional structures, the water commissioners, the engineering corps, the maintenance workers, that had kept them functional, the channels silted up, the pipes cracked, and the water stopped flowing. Rome's population collapsed along with its water supply. The city that had housed 1 million people in the 2nd century held perhaps 20,000 by the 7th century. The engineering knowledge that had built and maintained the aqueducts did not vanish overnight. Some of it was preserved in Vitruvius and other ancient texts that survived the fall of the West, copied in monastic scriptoria that valued ancient knowledge regardless of its immediate practical applicability. But the practical engineering tradition, the body of accumulated embodied knowledge of how to survey and build and maintain large infrastructure works, was disrupted by the collapse of the institutions and the economic and political systems that had sustained it. Medieval Europe built no aqueducts comparable to the Roman ones. Medieval European cities depended on wells, rivers, and rainwater collection, a regression in urban water supply that had direct consequences for public health, since rivers and wells in densely populated areas were inevitably contaminated. The great plagues of medieval Europe, including the Black Death, which killed 1/3 of Europe's population in the 14th century, were facilitated in part by the collapse of Roman sanitation infrastructure and the return to water supply systems that put drinking water in contact with human and animal waste. The knowledge of how to supply a 1-million-person city with clean water was lost. It was rediscovered gradually and laboriously during the Industrial Revolution of the 18th and 19th centuries, and the full achievement of Roman per capita water supply was not matched again in Europe until the late 19th century, roughly 1400 years after the last Roman aqueduct stopped flowing. Let us cross the world. Let us go east to the civilization that, more than any other single culture, produced the greatest range of fundamental technological innovations in the ancient and early medieval world, and that, paradoxically, is most consistently underrepresented in popular histories of technology, written from a European perspective. China. The list of Chinese technological firsts is so long and so fundamental that simply reciting it is humbling. Paper, not papyrus, but true paper, made from wood pulp or plant fibers, lightweight and cheap to produce, was invented in China around 105 CE. Block printing was developed in China during the Tang Dynasty, 618, 907 CE. Movable type was invented by the Chinese craftsman Bi Sheng around 1040 CE, 400 years before Gutenberg. The mechanical clock, with its escapement mechanism for regulating the movement of gears by controlled release rather than free running, was invented in China in the 8th and 9th centuries CE, centuries before its development in Europe. Cast iron, the production of iron in liquid form that can be poured into molds, was being practiced in China by the 4th century BCE, nearly 2 millennia before European iron masters developed the blast furnace technology that made cast iron possible in the West. And gunpowder. Chinese alchemists, working in the Tang Dynasty during the 9th century CE, discovered by what appears to have been an experimental accident that a mixture of charcoal, saltpeter, potassium nitrate, and sulfur ignited with explosive force when heated. They had been looking for an elixir of immortality. They found explosive powder. The irony is recorded in Chinese alchemical texts, which note with considerable dryness that the experimenters who worked with this mixture often died of burns. Within a century of this discovery, Chinese military engineers were using gunpowder in weapons, fire arrows, with gunpowder-filled bamboo tubes, fire bombs thrown by trebuchets, and eventually, in the 10th century CE, metal-barreled guns that could project projectiles by the force of the powder's explosion. The world's first guns were Chinese, and they preceded European cannons by several centuries. But here is what makes the Chinese story relevant to our theme of lost technology. China did not maintain all of its advantages. The magnetic compass, one of the most important navigational tools in human history, was invented in China, probably during the Han Dynasty, initially for geomantic divination purposes and later applied to navigation. Chinese navigators were using the compass for maritime navigation by the 11th century CE. This technology was eventually transmitted westward through Islamic intermediaries and transformed European navigation, enabling the age of exploration that began in the 15th century. But the Chinese themselves, who had the compass first and who possessed in the early 15th century the world's most powerful and sophisticated maritime technology, did not use it for global exploration. The great voyages of Zheng He, the Muslim eunuch admiral, who commanded an extraordinary fleet of enormous treasure ships and sailed from China to Southeast Asia, India, the Persian Gulf, and the East African coast in 7 voyages between 1405 and 1433 CE, were the greatest maritime enterprise in the world at that moment. Zheng He's largest ships were, by most estimates, longer than any European vessel built for another century. His fleet numbered hundreds of ships and carried tens of thousands of men. And then, in 1433, the voyages stopped. A faction at the Chinese imperial court, Confucian scholars who viewed maritime trade and foreign contact as socially disruptive and ideologically suspect, gained political influence and persuaded the Zhuangdi emperor to halt the voyages. The great ships were not maintained. The shipyards that had built them were allowed to fall into disrepair. The navigational charts and logs of the voyages were reportedly destroyed. Within a generation, the institutional knowledge of how to build and operate the treasure ships had been largely lost. China turned inward, and the global maritime stage was left to the Portuguese and Spanish, who would claim it definitively within a few decades. The political decision not to continue the voyages was, from a certain point of view, a rational response to a specific political situation within a specific cultural framework. The Confucian scholars who opposed the voyages were not ignorant or foolish. They had coherent arguments about social stability, resource allocation, and cultural values. But the long-term consequences included not only the abandonment of Chinese maritime expansion, but the loss of the specific technical knowledge, ship design, navigational practice, the accumulated experience of the open ocean that had been embodied in Zheng He's fleet. Knowledge that was not preserved in texts, not transmitted to apprentices, not maintained through continued practice. Knowledge that simply evaporated when the institutional context that had sustained it was dissolved by political decision. China's story is a reminder that technological regression is not always the result of catastrophic collapse. Sometimes it is the result of deliberate choice, of a society deciding, for reasons that seem compelling in the moment, that certain kinds of knowledge and capability are not worth maintaining. And sometimes those decisions turn out to be irreversible. We spoke at length about the Antikythera mechanism in our second chapter, and we established that it represents the surviving example of what must have been a broader tradition of mechanical precision instrumentation in the ancient Greek world. Let us now explore what else that tradition may have contained. The hints and suggestions and partial evidence of a world of ancient mechanisms that has been almost entirely lost to time. The ancient literary record contains intriguing references to devices that, if they existed as described, would represent mechanical sophistication comparable to, or exceeding, the Antikythera mechanism. Hero of Alexandria, the first-century Greek mathematician and engineer working in Roman Egypt, is one of the most remarkable figures in the history of technology. In addition to the steam-powered rotating sphere mentioned earlier, Hero designed and described a programmable cart, a wheeled vehicle whose steering and stopping were controlled by a rope wound around its axle in a pattern that could be configured before departure to produce any desired path. The cart would travel forward a certain distance, turn, travel again, turn again, following a pre-programmed route, without any external guidance. This is, in functional terms, an analog computer for mechanical motion control, precisely the concept behind modern computerized numerical control in manufacturing. Hero also designed the world's first vending machine, a device that dispensed a measure of holy water when a coin was inserted into a slot, the coin's weight triggering a lever mechanism that opened a valve and dispensed the water before closing it again automatically. And he designed several elaborate theatrical automata, programmable mechanical devices that could perform sequences of actions in response to counterweighted falling balls, producing dramatic performances of mechanical motion that ancient audiences apparently found genuinely entertaining. How many of these devices were built? How widely were they used? We do not know. Hero's descriptions suggest a working engineer describing devices he has actually built, not a theorist describing what might be possible in principle. But the texts that preserve his descriptions were copied by monastic scribes in the medieval period because they were considered interesting natural philosophy, not because they were considered practical engineering manuals. The practical tradition that would have associated his textual descriptions with actual working devices was gone by the time the texts were being copied. Archimedes of Syracuse, living in the 3rd century BCCE, and considered by many the greatest mathematician of the ancient world, is described by ancient sources as having built working mechanical models of the solar system, devices that track the movements of the sun, moon, and planets, presumably using the same general principles as the Antikythera mechanism. Cicero, the same Roman orator who mentioned having seen the device of Posidonius, also claims to have seen, in Marcellus's house in Rome, a model made by Archimedes that his descendants still possessed. He describes it as showing when set in motion, the movements of the moon and sun, and the 5 planets at every turn, exactly as they occur in the sky. If Archimedes built such a device, and if Cicero's description is accurate, then the Antikythera mechanism is not the oldest surviving example of its type. It is one of several comparable devices that were being made over a period of at least 2 centuries by the greatest mathematical minds of the Greek world. The tradition was not a single flash of genius, but an extended tradition of mechanical astronomy. What else might have been part of that tradition? Ancient sources describe the great bronze statue of Helios at Rhodes, the Colossus of Rhodes, which stood over the harbor of the same city, where the Antikythera mechanism was likely made, as incorporating mechanical elements, a torch whose flame was maintained by internal mechanisms, perhaps rotating elements. The Colossus was destroyed by an earthquake around 226 BCE and was not rebuilt, so we cannot know whether these descriptions reflect reality or embellishment, but they are consistent with what we know of the mechanical sophistication of Rhodian craftsmen. There are references in ancient sources to mechanical singing birds, mechanical statues that appeared to speak, elaborate hydraulic organs, automated theater stages, and door-opening mechanisms activated by fire. Not all of these references are credible. Ancient writers were not immune to the human tendency to embellish an impressive story, but the concentration of such references in the Hellenistic and Roman periods, and their consistency with what we know the ancient world could actually produce, suggests that mechanical devices, automata, instruments, machines of various kinds, were more common in the ancient world than the surviving material evidence would suggest. The material evidence is sparse simply because metal is valuable and was recycled. When the economy of a region collapsed or changed, the metal in its precision instruments, the carefully cut bronze gears, the precisely turned axles, the worked springs and levers, was melted down for other uses. The bronze went back into the ground in a different form, or into a new sword, or into a different machine. Only the Antikythera mechanism survived because its chips sank to the bottom of the sea before the metal could be reclaimed, and the sea protected it from the recycler's crucible for 2,000 years. What we see in the Antikythera mechanism is not an anomaly. It is a survivor, the last representative of a world of ancient precision mechanics that the accident of the seafloor preserved while everything else was lost. We have been moving through the ancient world, gathering examples of lost knowledge, encountering the same pattern again and again, in different forms. Something remarkable was built, something extraordinary was understood, and then, through processes that varied in their specifics, but shared certain deep structural similarities, the knowledge was lost. Now, let us turn the lens inward. Let us ask not what was lost, but why. Why do civilizations lose knowledge? What are the mechanisms of technological forgetting? And what does the answer tell us about the nature of human knowledge itself? The first and most fundamental insight is that knowledge is not a thing. It is not a substance that can be stored in a jar or buried in a vault and recovered intact generations later. Knowledge is a process, a living, dynamic process that exists only in the relationship between minds and the world. It exists in the act of practice, of transmission, of use. When the practice stops, when the transmission chain is broken, when the use disappears, the knowledge does not remain dormant, waiting to be revived. It degrades. It becomes incomplete. It becomes uninterpretable. It dies. This is particularly true of the kind of knowledge most relevant to ancient technology: practical, tacit knowledge. Tacit knowledge, the term coined by the philosopher Michael Polanyi, is knowledge that you cannot fully articulate, that lives in the body rather than the intellect. that is transmitted through demonstration and apprenticeship rather than through verbal instruction or text. A master smith who knows how to identify the correct temperature for quenching a Damascus steel blade by the color of the glow has tacit knowledge that is almost impossible to transmit in writing. Heat until bright orange does not convey what bright orange looks like in a dim workshop, or how it looks different from the orange of slightly too hot or slightly too cool, or how the experienced eye perceives subtle differences in shade that the inexperienced eye sees as identical. This kind of knowledge lives in the visual cortex and the motor memory of the craftsman, not in language, and it can only be transmitted by watching an expert do it, repeatedly, under conditions close enough to real practice, to allow the observing brain to calibrate itself against the expert's performance. When the chain of master to apprentice transmission is broken, when there are no more masters, or when the social and economic conditions that sustain the master-apprentice relationship disappear, this kind of knowledge cannot be recovered from texts. It has to be rediscovered, from scratch, by a new generation of experimenters who must work their way back to the same understanding through trial and error. And the rediscovery process may take decades or centuries, even when the textual descriptions of the desired result survive. The history of attempts to rediscover Roman concrete illustrates this exactly. Modern materials scientists had the surviving concrete to analyze. They had Vitruvius descriptions of the materials and the method, but it took decades of analytical chemistry, molecular-level imaging, and careful experimental work to understand the mechanism that makes the concrete perform the way it does, and the full picture is still not entirely clear. The knowledge of what to do was recoverable from the surviving material evidence and the textual descriptions. The knowledge of why it works took modern chemistry to understand, and neither the what nor the why is sufficient by itself. You also need the practical knowledge of how to do it, how to mix the materials in the right proportions, how to tell when the mix is right, how to manage the setting process, which is tacit knowledge that must be rediscovered through practical experimentation. The second mechanism of knowledge loss is institutional collapse. Most of the extraordinary knowledge we have been discussing was maintained not by individuals, but by institutions. The Mouseion at Alexandria, the engineering corps of the Roman army, the system of Rhodian mechanical craftsmen, the Gurukul system of ancient India. These institutions were not merely places where individual experts happened to congregate. They were systems, social technologies for the preservation and transmission of knowledge, the accumulation of successive generations' contributions, and the coordination of expertise in the service of large-scale projects. When institutions collapse, when they lose their funding, their political protection, their physical security, their social legitimacy, they do not merely shut down, they dissolve. The accumulated knowledge they held, in their physical libraries, in the heads of their practitioners, in the social networks of master-apprentice relationships, in the institutional practices and routines that organized and transmitted what was known, disperses and degrades. Some of it finds refuge in other institutions or in the memories and notes of individual survivors who scatter to other places. Much of it simply vanishes. The specific catastrophes that trigger institutional collapse vary. Military conquest, epidemic disease, economic collapse, political revolution, ecological crisis. The Roman Empire's collapse in the West was driven by a combination of all of these. Military pressure from Germanic peoples, economic disruption, epidemic diseases that reduced the population and the tax base, ecological changes that reduced agricultural productivity, and political fragmentation that made coordinated response increasingly impossible. But the institutional collapse that resulted was not simply the end of a set of buildings or a set of political structures. It was the end of the social systems that had transmitted and preserved a vast body of practical knowledge. And the knowledge, lacking its institutional container, did not survive intact. The third mechanism of knowledge loss is what we might call the complexity trap. Highly sophisticated technology often requires a complex supporting system of prerequisite knowledge, materials, skills, and infrastructure. The more complex the supporting system, the more vulnerable the technology is to the failure of any one of its components. Roman concrete required not just the formula, but access to specific volcanic ash from specific sources, knowledge of how to identify the right ash from similar-looking but inferior materials, the ability to mix and apply it correctly, and the institutional context, the public works departments, the skilled contractors, the experience of previous projects that maintained all of these prerequisites. When the system supporting the technology became fragmented, the technology became inaccessible even to people who, in principle, still knew what it required. This complexity trap affects modern technology too. There are technologies developed in the mid-20th century that we have difficulty reproducing today, not because the knowledge has been lost in any simple sense, but because the specific supply chains, manufacturing infrastructures, and trained workforces that supported them have been dissolved, and reconstituting them would require more investment than it appears worth for limited applications. The Saturn V rocket that carried humans to the moon. Could we build it again? In principle, yes. In practice, several of the specific manufacturing processes and materials have not been used in decades. The engineers who designed and built them have retired or died. The production facilities have been converted to other uses, and the reconstitution of the full system would be a major engineering project requiring years and significant resources. We are not as immune to the complexity trap as we sometimes assume. The fourth mechanism is deliberate secrecy. We have already discussed this in the context of Greek fire. Some technologies are held as secrets by the individuals or institutions that develop them because the competitive or military advantage they provide is dependent on others not having access to them. Secrets that are not written down, that are transmitted only orally within small, trusted groups, are extraordinarily vulnerable to the loss of those groups. The Venetian glass-blowing tradition, technically not ancient but illustrative, was maintained as a state secret by the Republic of Venice for centuries, with glassmakers confined to the island of Murano, and their emigration from Venice legally prohibited under pain of death. The Republic understood that its dominance of the luxury glass market, which was a significant source of wealth, depended on preventing its craftsmen from taking their knowledge to competitors. The strict secrecy worked commercially for the purposes intended, but it also meant that if a catastrophe had hit Venice, a plague, an invasion, an earthquake, the knowledge could easily have been permanently lost. The deliberate concentration of specialized knowledge in small, geographically concentrated groups, while rational from the secrecy standpoint, is inherently fragile from the preservation standpoint. The same logic that keeps competitors from stealing the knowledge also keeps the knowledge from being distributed widely enough to survive the loss of its keepers. These four mechanisms, the tacit nature of practical knowledge, institutional collapse, the complexity trap, and deliberate secrecy, between them, explain most of the losses we have been exploring. They are not unique to the ancient world. They are structural features of how human knowledge works, in any era, and they remain active today, which raises a disquieting question for the late-night listeners settling into sleep. What are we losing right now, in our own civilization, through these same mechanisms? What knowledge that seems solid and permanent today is actually more fragile than it appears? The answer is probably more than we think. Not all ancient technological mysteries are fragmentary, incomplete, or known only from second-hand descriptions. Some of them stand in full view, in public places, being visited by thousands of people every day, while quietly defying explanation. In the courtyard of the Quwat-ul-Islam Mosque, in the Qutb Minar complex, in Delhi, India, there stands an iron pillar. It is about 7 meters tall. Its lower portion is fluted, its upper portion plain. It weighs approximately 6 tons. An inscription near its base, in the Sanskrit Brahmi script, used in the Gupta period, dedicates the pillar to the Hindu god, Vishnu, and celebrates the military victories of a king named Chandra, almost certainly Chandragupta II, who ruled the Gupta Empire from approximately 375 to 415 CE. The pillar has been standing in the open air of Delhi for roughly 1600 years, and it is not rusting. An iron pillar of this size, standing outdoors in a tropical environment with a significant monsoon season, should be substantially corroded after 1600 years. Ordinary iron in these conditions would be largely reduced to rust within a few centuries, and yet the Delhi iron pillar shows only minimal surface oxidation, a thin dark brown coating that is not ordinary rust, but a stable protective layer of iron hydrogen phosphate hydrate, a compound whose formation requires specific conditions of cycling humidity and temperature. This protective layer, known in materials science as a passive oxide layer or rust passivation layer, forms on the surface of the iron and prevents further oxidation from reaching the iron beneath. It is in effect a natural corrosion protection mechanism, analogous to the protective oxide layer that forms on aluminum and gives aluminum its corrosion resistance. What makes the Delhi pillar remarkable is not that this mechanism exists, it is known to modern materials science, but that the Gupta period Indian metallurgists who made the pillar appear to have deliberately induced it. Analysis of the pillar's iron has found that it has an unusually high phosphorus content, between 0.1 and 0.25% phosphorus, compared to the trace amounts found in most historical iron artifacts from other cultures. This high phosphorus content is the key to the formation of the protective layer. It is the phosphorus that drives the formation of iron hydrogen phosphate hydrate, rather than ordinary rust. High phosphorus iron is not the natural product of standard iron smelting. It requires either a specific source of ore with naturally high phosphorus content, or, more likely, a deliberate smelting practice that retained phosphorus from the ore or added it from other sources. The ancient Indian metallurgists who made the Delhi pillar knew, at some level, that their process produced iron of unusual quality and durability. Whether they understood the chemistry of why, whether they knew that the phosphorus was responsible, is unknown and unlikely. What they had was the embodied craft knowledge of a process that worked, producing iron, whose performance in the world was observably superior to ordinary iron. The knowledge of how to achieve this specific iron composition and microstructure was part of the ancient Indian metallurgical tradition, a tradition of extraordinary sophistication that also produced wood steel, and that had been developing in the subcontinent for over 3,000 years by the time the Delhi pillar was made. The same tradition produced, in different geographical regions of India, iron artifacts of various types and scales. The iron beams in the Konark Sun Temple in Odisha, a structure built in the 13th century CE, include iron beams of unusual purity and composition that have survived 8 centuries of the harsh coastal environment of the Bay of Bengal with minimal corrosion. The specific metallurgical knowledge that produced these remarkable iron artifacts does not appear in any surviving textual source in explicit, recoverable form. Like so much ancient technical knowledge, It was practical and tacit, held in the fingers and eyes of the smiths who worked the iron, transmitted through generations of practice, observable in its results, but not reducible to a formula that could survive independent of the practice itself. The practice was eventually disrupted by the Muslim invasions of the 10th through 13th centuries AUE, which destroyed temples and technical schools and disrupted the social structures that had sustained specialized craft traditions, by the economic changes brought by European trade and colonialism in subsequent centuries, by the gradual replacement of traditional craft metalworking by industrial production. The pillar stands. The formula that produced it is gone. Every day, thousands of visitors circle it in the Qutb Minar complex, touching its cool, smooth, slightly oily surface, and rarely thinking about what they are touching. 16 centuries of patient chemical self-maintenance, the visible embodiment of a knowledge tradition that no longer exists. Not all ancient technological mysteries are fragmentary, incomplete, or known only from second-hand descriptions. Some of them stand in full view, in public places, being visited by thousands of people every day, while quietly defying explanation. In the courtyard of the Quwwat-ul-Islam Mosque, in the Qutb Minar complex, in Delhi, India, there stands an iron pillar. It is about 7 meters tall. Its lower portion is fluted, its upper portion plain. It weighs approximately 6 tons. An inscription near its base, in the Sanskrit Brahmi script, used in the Gupta period, dedicates the pillar to the Hindu god, Vishnu, and celebrates the military victories of a king named Chandra, almost certainly Chandragupta II, who ruled the Gupta Empire from approximately 375 to 415 CE. The pillar has been standing in the open air of Delhi for roughly 1600 years, and it is not rusting. An iron pillar of this size, standing outdoors in a tropical environment with a significant monsoon season, should be substantially corroded after 1600 years. Ordinary iron in these conditions would be largely reduced to rust within a few centuries, and yet the Delhi iron pillar shows only minimal surface oxidation, a thin dark brown coating that is not ordinary rust, but a stable protective layer of iron hydrogen phosphate hydrate, a compound whose formation requires specific conditions of cycling humidity and temperature. This protective layer, known in materials science as a passive oxide layer or rust passivation layer, forms on the surface of the iron and prevents further oxidation from reaching the iron beneath. It is in effect a natural corrosion protection mechanism, analogous to the protective oxide layer that forms on aluminum and gives aluminum its corrosion resistance. What makes the Delhi pillar remarkable is not that this mechanism exists, it is known to modern materials science, but that the Gupta period Indian metallurgists who made the pillar appear to have deliberately induced it. Analysis of the pillar's iron has found that it has an unusually high phosphorus content, between 0.1 and 0.25% phosphorus, compared to the trace amounts found in most historical iron artifacts from other cultures. This high phosphorus content is the key to the formation of the protective layer. It is the phosphorus that drives the formation of iron hydrogen phosphate hydrate, rather than ordinary rust. High phosphorus iron is not the natural product of standard iron smelting. It requires either a specific source of ore with naturally high phosphorus content, or, more likely, a deliberate smelting practice that retained phosphorus from the ore or added it from other sources. The ancient Indian metallurgists who made the Delhi pillar knew, at some level, that their process produced iron of unusual quality and durability. Whether they understood the chemistry of why, whether they knew that the phosphorus was responsible, is unknown and unlikely. What they had was the embodied craft knowledge of a process that worked, producing iron, whose performance in the world was observably superior to ordinary iron. The knowledge of how to achieve this specific iron composition and microstructure was part of the ancient Indian metallurgical tradition, a tradition of extraordinary sophistication that also produced wood steel, and that had been developing in the subcontinent for over 3,000 years by the time the Delhi pillar was made. The same tradition produced, in different geographical regions of India, iron artifacts of various types and scales. The iron beams in the Konark Sun Temple in Odisha, a structure built in the 13th century CE, include iron beams of unusual purity and composition that have survived 8 centuries of the harsh coastal environment of the Bay of Bengal with minimal corrosion. The specific metallurgical knowledge that produced these remarkable iron artifacts does not appear in any surviving textual source in explicit, recoverable form. Like so much ancient technical knowledge, it was practical and tacit, held in the fingers and eyes of the smiths who worked the iron, transmitted through generations of practice, observable in its results, but not reducible to a formula that could survive independent of the practice itself. The practice was eventually disrupted by the Muslim invasions of the 10th through 13th centuries AUE, which destroyed temples and technical schools and disrupted the social structures that had sustained specialized craft traditions, by the economic changes brought by European trade and colonialism in subsequent centuries, by the gradual replacement of traditional craft metalworking by industrial production. The pillar stands. The formula that produced it is gone. Every day, thousands of visitors circle it in the Qutb Minar complex, touching its cool, smooth, slightly oily surface, and rarely thinking about what they are touching. 16 centuries of patient chemical self-maintenance, the visible embodiment of a knowledge tradition that no longer exists. Let us sit for a moment with the most radical question in the study of ancient technology. Not a question I can definitively answer, and not one for which the conventional archaeological mainstream accepts any non-trivial answer, but a question that the evidence we have been examining throughout this journey seems to keep pushing us toward. Is it possible that the period we call prehistory, the era before writing, before the recognized ancient civilizations of Egypt, Mesopotamia, the Indus Valley, and China, contained levels of technological and social sophistication that we have not yet recognized, and whose evidence we have not yet found? The conventional view of human prehistory is a story of gradual accumulation. Hunter-gatherers gradually developing agriculture, small communities gradually growing into villages, then towns, then cities, pottery, then metalworking, then writing. Each step building on the previous, the pace accelerating over time, the overall trajectory one of steady, if sometimes interrupted progress, from simple to complex. This view is well supported by the archaeological evidence we currently have, but it rests on an assumption that requires examination, that the evidence we have is representative of what existed. The problem with prehistoric evidence is its extraordinary fragility. Most of what any society produces does not survive in the archaeological record. Wood rots, fabric disintegrates, leather dissolves, paper, parchment, bark, leaves. Any writing or recording medium, derived from organic materials, disappears within centuries or millennia, unless preserved in exceptional conditions. The extreme aridity of Egyptian tombs, the anaerobic bogs of northern Europe, the dry cold of Siberian permafrost. What survives is stone, fired ceramic, and metal, the hardest, most durable materials. And even these survive only in certain conditions, and only if they have not been subsequently recycled. If a sophisticated civilization existed 12,000 or 15,000 years ago, before the youngest, driest cooling event that ended around 11,500 years ago. In a world whose coastlines were quite different from today's, because sea levels were significantly lower during the glacial maximum, we might expect to find very little physical evidence of it. Most of its coastal settlements, which is where most settlements in most eras have been located, because proximity to maritime resources and trade routes is such a consistent factor in the growth of complex societies, would be underwater, covered by the sea level rise of the post-glacial period. 100 meters of ocean water is a very effective archaeological barrier. Göbekli Tepe, the remarkable complex of carved stone pillars in southeastern Turkey, has genuinely disrupted the conventional timeline of social development. This site, dating to approximately 11,000 to 9,000 BCE, making it the oldest known monumental architecture in the world by several thousand years, was built by people who were, by conventional archaeological criteria, still hunter-gatherers. There is no evidence of permanent settlement at the site itself. It appears to have been a gathering place for a mobile or semi-mobile population. Yet its construction required the coordinated effort of large numbers of people over extended periods, and the carved reliefs on its pillars show sophisticated artistic ability and symbolic thinking. Göbekli Tepe was deliberately buried around 8,000 BCE. The pillars were carefully filled in with rubble and debris, preserving them remarkably well, in a process whose purpose is entirely unclear. It had been underground for 10,000 years before its excavation beginning in the 1990s. Its existence was completely unknown and completely unsuspected before it was found. How many Göbekli Tepes are there, still underground, still unexcavated, still unknown? The answer is, we don't know. But the probability is that there are more. The archaeological survey of the Earth's land surface is far from complete, and the survey of the ocean floor, where a significant portion of the prehistoric world's coastlines now lie, has barely begun. The evidence we have tells us that human beings were capable of significant social coordination, large-scale construction, and sophisticated symbolic thought far earlier than was previously believed. The Göbekli Tepe finding has forced a genuine revision of the standard model of the transition from hunter-gatherer to complex society, a revision that is still being worked out, with new evidence still coming in. What the evidence does not tell us, and what remains speculative, is whether any pre-agricultural culture achieved anything comparable to the technological sophistication we have been examining in this journey. The Antikythera mechanism required millennia of accumulated mathematical and astronomical knowledge. The Roman concrete required centuries of empirical building experience. The Damascus steel required a specific metallurgical tradition developed over a long period. These achievements were possible in the historical civilizations we know about because of the institutional structures and accumulated knowledge that those civilizations had built up over long periods. Could a prehistoric culture, lacking writing and metal, and the large cities that archaeology traditionally associates with complex civilization, have developed comparable knowledge through different means? The honest answer is, we don't know. We cannot rule it out. The evidence that would confirm or deny it largely does not exist, either because it never existed in durable form, or because it is on the bottom of the ocean, or because it is underground, waiting to be found. What we can say is that every time we have assumed a lower bound on ancient human capability, assumed that people before a certain date or without certain technological markers could not have done or known certain things, the evidence has eventually contradicted the assumption. Hunter-gatherers should not, by the conventional model, have built Göbekli Tepe. They built it anyway. Human intelligence, curiosity, problem-solving capacity, and the ability to accumulate and transmit knowledge did not arise with the invention of writing or the building of cities. They are evolved capacities that have been present in Homo sapiens for at least 300,000 years. What writing and cities provide is a better infrastructure for the accumulation and transmission of knowledge. But infrastructure and capacity are not the same thing. The deep past is darker than we would like, but the darkness is not emptiness, it is unknown territory. And unknown is not the same as empty. We have traveled far tonight. We have stood in the cold green depths of the Aegean Sea and watched a bronze mechanism model the universe with patient precision. We have walked the geometry of the Giza Plateau and felt the weight of 4,500 years pressing against the stone. We have followed the chemistry of Roman harbor walls as the sea slowly made them stronger, and traced the loss of the formula that created them through the long unraveling of an empire. We have bent over ancient maps and puzzled at their impossible knowledge, examined a Baghdad clay jar, and wondered what its makers understood about electricity, watched Greek fire burn on the surface of the sea and then go dark forever. We have sat with the great library's long, slow dissolution, felt the absence of Zheng He's armada as it turned back from the global ocean, traced the nanotube structures in a medieval Damascus blade that its maker did not know were there. And now, in the final chapter of this long night's journey, let us sit quietly with the question that all of these stories, together, seem to be asking. What is the conversation that runs through all of this? Every ancient technology we have examined tonight was not simply a tool or a technique. It was a form of thought made visible, a thought about the world, about how the world works, about what human beings can do within it when they apply intelligence and patience and accumulated knowledge with sufficient discipline and care. The Antikythera mechanism is a thought about the regularity of the cosmos, made in bronze. The pyramids are a thought about geometry and permanence, made in stone. Roman concrete is a thought about materials and chemistry, made in harbor walls. Damascus steel is a thought about the relationship between structure and function, made in iron. These thoughts were lost, for the most part, not because they were wrong. Many of them were more right than what replaced them, but because the conditions that had allowed them to develop and persist were disrupted. The institutional containers that held the knowledge broke open. The transmission chains between generations were severed. The economic and political systems that had funded the specialized labor of knowledge production were replaced by other systems with different priorities. And yet the thoughts themselves, the underlying truths about the world that the ancient craftsmen and scientists had reached, did not go away. They were always there, in the materials and the physics and the chemistry of the world, waiting to be rediscovered. The volcanic ash of Puteoli still had the same mineral composition in the medieval period as it did in the Roman period. The iron-hydrogen phosphate chemistry that protected the Delhi pillar was still operating in the medieval period, whether or not anyone understood it. The lunar cycles that the Antikythera mechanism tracked continued to repeat in the same pattern, whether or not any bronze gears were modeling them. The truths were always available. What was lost was the human relationship with those truths, the specific forms of attention and practice through which particular communities of people had developed access to them. And this is perhaps the most important thing that the ancient technological mysteries can teach us, that the relationship between human knowledge and truth is not automatic. It is not guaranteed. It requires constant cultivation, constant effort, constant renewal. Knowledge does not take care of itself. Civilizations do not automatically preserve their best achievements. The accumulation of understanding across generations is a project that must be actively maintained through institutions, through education, through the deliberate transmission of practical know-how as well as theoretical concepts. The ancients lost so much because the conditions that had allowed the accumulation of their knowledge did not last. Their empires fell, their institutions collapsed, their cities emptied, and their forests grew back over their ruins. This is not a failure of intelligence or capability on their part. It is the universal condition of civilizations. They are impermanent. They rise, they achieve, and they fall. And the achievement is often more fragile than it appears in its flourishing. But here is what is also true. Much of what was lost has been found again. The principles of Roman concrete were not gone from the world. They were gone from human knowledge. The chemistry that makes pozzolanic concrete so remarkable was in the volcanic ash all along. Modern scientists found it again through the application of precisely the same qualities of intelligence and patient observation that the original Roman engineers had applied 2,000 years earlier. The route was different: electron microscopes and X-ray crystallography, rather than empirical building experience. But the destination was the same truth. Every rediscovery of ancient knowledge is a form of conversation across time. The ancient craftsman and the modern scientist are reaching toward the same truths from different angles, using different tools, in different eras, and occasionally their hands meet across the centuries. The Roman harbor builder and the Berkeley materials scientist, the Gupta period smith and the modern metallurgist, the ancient Rhodian gear cutter and the 21st century X-ray crystallographer. They are all in the same conversation, about the same world, working with the same human capacity for curiosity and pattern recognition, and the desire to understand. This conversation is what civilization is at its best and most enduring. Not the buildings or the roads or the harbor walls. Those are its products, and like all products, they decay. The conversation itself is what persists, the human project of figuring out how the world works, building on what previous thinkers have figured out, preserving what can be preserved, and rediscovering what is lost. Tonight, as you drift toward sleep, with the ancient world still echoing in your mind, hold this thought gently. You are part of that conversation. Every curious person who reads about the Antikythera mechanism, or the pyramids, or Roman concrete, who feels the particular quality of wonder that comes from encountering genuine human achievement across the gulf of centuries, that person is extending the conversation forward, keeping it alive, adding their attention to the chain of attention that connects the ancient craftsman to the unimaginable future. The mechanisms are lost, but the making of them, the intention, the intelligence, the slow, patient accumulation of understanding, that is not lost. That lives in us, because we are made of it. We are the latest iteration of the same species that cut those bronze gears and mixed that volcanic ash, and found, in the regularities of the sky, and the properties of materials, and the geometry of stone, reasons for wonder, and subjects for thought. The ancient world did not achieve what it achieved because its people were different from us. They achieved it because they were exactly like us, curious, persistent, capable of both extraordinary brilliance and extraordinary short-sightedness, but in a different world, with different tools and different institutions and different cultural priorities. What they made in their world, with their tools, speaks to us, across the centuries, not as a lesson in how much we have lost, though we have lost much, but as a reminder of what we are, a species uniquely capable of building knowledge across generations, uniquely vulnerable to losing it, and uniquely capable of finding it again. The stars that the Antikythera mechanism was built to track are still above you, right now, turning in their ancient courses, indifferent to empires, waiting for the next person who decides to pay attention. As you close your eyes more fully now, let the images of this long night settle gently. the bronze gears turning in the dark water, the pale limestone of the pyramid at dawn, the Roman harbor standing in the Mediterranean tide, the Polynesian navigator reading the ocean with his whole body. Let them soften into the background of your mind, taking their place alongside everything else that this remarkable species has built and lost and built again. You have been in the company of human genius tonight. Carry it gently into sleep. Let your breathing slow and rest in the ancient, continuous, never-finished conversation